Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi at Delhi. Today we are going to discuss about a module called Introduction to Nonlinear Optics. It comes under the paper entitled Characterization of Materials 2. So, students, let us see what we are going to learn in this module. First is that the fundamentals of light progression will be discussed, the polarization of light for constraining the components of the unpolarized light to propagate to a component in a specified direction will be discussed, and we will be understanding various processes and techniques to observe the linearly, circularly and elliptically polarized lights. In introduction, optics is a branch of physics that deals with the behavior and properties of light, including its interaction with matter and the construction of instruments that uses to detect it. Optics usually describes the behavior of visible, ultraviolet and infrared light. Because light is an electromagnetic wave, other forms of electromagnetic radiation such as X-rays, microwaves and radio waves exhibit similar properties. When we consider the particle-like properties of light, we generally model the light as a collection of particles called photons, which are also referred as the quanta of light. Quantum optics deals with the application of quantum mechanics to optical systems. Practical application of optics are found in a variety of technologies and everyday objects, including mirrors, lenses, telescopes, microscopes, lasers, and fiber optics. A major subfield of modern optics, quantum optics, deals with specifically quantum mechanical properties of light. Quantum optics is not just theoretical. Some modern devices such as lasers have principles of operation that depends on quantum mechanics. Light detectors such as photomultipliers and channeltrons respond to individual photons. The electronic image sensors such as CCDs exhibit short noise corresponding to the statistics of individual photon events. The light emitting diodes and photovoltaic cells too cannot be understood without quantum mechanics. In the study of these devices, quantum optics often overlaps with quantum electronics. Special research areas of optics include the study of how light interacts with specific materials as in crystal optics and metamaterials. The electromagnetic waves such as light traveling in free space or another homogeneous isotropic non-attenuating medium are properly described as transverse waves, meaning that a plane wave, the electric field vector E and the magnetic field H are in directions perpendicular to transverse to the direction of the wave propagation, and E and H are also perpendicular to each other. In the linear optics is the branch of optics that describes the behavior of light in linear media, that is, the polarization of light is linearly proportional to the electric field. So, P is directly proportional to E over here, and the electromagnetic waves and the nonlinear optics is the study of phenomena that occur as a consequence of the modification of the optical properties of a material system by the presence of light. The nonlinear optics is the branch of optics that describes the behavior of light in nonlinear media, that is, the polarization of light is not proportional to the electric field. In this chapter, we will discuss and understand the nonlinear behavior of light. Unpolarized light. A light is a wave that propagates in all directions. Photon is the quanta of light and exhibits electromagnetic wave that vibrates in a variety of directions. The light propagated in a given direction consists of independent waves whose planes of vibration are randomly oriented perpendicular to the direction of propagation. Light propagation in more than one plane is termed as unpolarized light, and this is schematized in figure 1. Light emitted by the sun, by a lamp, or by a candle flame are the examples of unpolarized light. The arrows in the figure represent the direction of propagation of the light waves, the vibrations. The randomly oriented plane waves produce symmetry about the direction of propagation. Polarization is a property of waves that propagates in a specifically defined orientation. Radio waves and radar waves are also electromagnetic waves which are resulting from a surging dipole charge up and down. This kind of electromagnetic waves are not randomly generated, not symmetric, and prefer non-symmetric orientations of the electric and magnetic oscillations relative to the direction of propagation. Such kind of waves are referred as polarized. Randomly oriented waves could be polarized by placing a polarizer on the way of the unpolarized light as schematized in figure 2. Most sources of light are incoherent and unpolarized or only partially polarized because they consist of a random mixture of waves having different frequencies, wavelengths, phases, and polarization states. Randomly oriented waves such as electromagnetic waves, gravitational waves could be polarized because these waves are transverse waves, and these transverse waves are normally the waves that oscillates perpendicular to the direction of propagation. The waves that inherently oscillates in the direction of the propagation, such as sound waves in a gas or liquid, could not be polarized because sound waves are longitudinal waves, and longitudinal waves are the waves that oscillates along the direction of propagation. Let us discuss the origin of nonlinear optics. When light wave propagates through an optical medium, the oscillating electromagnetic field exerts a polarizing force on all the electrons in a medium. Since the inner electrons of the atoms are tightly bound to the nuclei, the major polarizing effect is exerted on the outer or valence electrons. With the excitation of ordinary light sources through a medium, the radiation fields created by the incident lights are much smaller than the fields that bind the electrons to the atoms of the medium. Hence, radiation acts as a small perturbation. The magnitude is about 10 to the power 8 volt per meter. This produces a polarization that is proportional to the electric field of the light wave. That means P is directly proportional to E. The light wave with such a low intensity cannot affect the atomic fields of the extent that could change the optical parameters such as refractive index, intensity, absorption coefficient, frequency, etc. However, if the radiation field is comparable with the atomic fields, that is by laser radiation, then the relation between the polarization and radiation field E is no longer linear. So, P is not directly proportional to E in this case. So, we can define a different branch of optics called nonlinear optics that describes the behavior of light in nonlinear media, that is, media in which the dielectric polarization P responds nonlinearly, nonlinearly to the electric field E of the light. This nonlinearity is typically observed at very high light intensities. That means the values of the electric field is comparable to the interatomic electric fields, which is typically 10 to the power 8 volt per meter, such as those provided by the laser lights. Polarization is a phenomenon where the waves that vibrate in a direction perpendicular to their direction of the propagation, that is referred as transverse waves. Light is a transverse electromagnetic wave. In an electromagnetic wave, both the electric and magnetic field oscillates in different directions. Light propagates as a plane wave in free space and as a transverse wave in an isotropic medium. Both the electric and magnetic fields are perpendicular to the wave's direction of travel and are the transverse waves. The oscillation of these fields can be in any direction. It may be in a single direction, generally termed as linear polarization, or it may be rotated at an optical frequency called circular or elliptical polarization. So, we will study about the linear polarization, circular polarization and elliptical polarization differently with schematic diagrams. First, the linear polarization. In electrodynamics, linear polarization or plane polarization of electromagnetic radiation is a confinement of the electric field vector or magnetic field vector to a given plane along the direction of propagation. When the original unpolarized light passes through the linear polarizer, the system allows light to oscillate in one direction as schematized in the diagram. The second one is circular polarization. In electrodynamics, this circular polarization of an electromagnetic wave is the confinement in which the electric field of the passing wave doesn't change the strength but only changes the direction in a rotary manner. Here, the strength and the direction of an electric field is defined as electric field vector in circularly polarized wave as shown in the diagram. At a given point in space, the tip of the electric field vector describes a circle as time progresses. If the wave is frozen in time, the electric field vector of the wave describes a helix along the direction of propagation. The third one is the elliptical polarization. This can be defined as the confinement of electromagnetic radiation such that the tip of the electric field vector describes an ellipse in any fixed plane intersecting and normal to the direction of propagation. An elliptically polarized wave may be resolved into two linearly polarized waves in phase quadrature with their polarization planes at right angles to each other. Since the electric field can rotate clockwise or counterclockwise as it propagates, elliptically polarized waves exhibits chirality. Now, let us discuss how to produce the polarized light. It can be produced by four ways. First way is the wire grid polarizer and the Polaroid. Second, by using polarization by reflection. Third is the polarization by double refraction, and fourth is the polarization by scattering. So, we will be discussing in next slides about all these four techniques used to produce the polarized light. The wire grid polarizer and the Polaroid. The wire grid polarizer essentially consists of a large number of thin copper wires placed parallel to each other. When an unpolarized electromagnetic wave is incident on it, then the component of the electric vector along the length of the wire is observed. This is due to the energy associated with the electric field which is lost in Joule heating of the wires. Since it is extremely difficult to fabricate a wire grid polarizer which would be effective for visible light, one may employ long chain polymer molecules with high conductivity along the length of the chain, aligned almost parallel to each other. Because of high conductivity provided by atoms in molecules, the electric field parallel to the molecules get observed. A sheet containing such chain molecules is known as Polaroid. Polarization by reflection. Let us consider the incidence of a plane wave on a dielectric. Assume that the electric field vector associated with the incident wave lies in the plane of incidence. Here, according to Brewster's law, the angle theta p is equal to tan inverse n1 divided by n2, where n1 and n2 are the refractive indices of two different mediums. At this angle of incident, the reflected and the transmitted rays are at right angles to each other, and the angle theta p is known as the polarizer or Brewster's angle. If the angle of incidence theta is equal to theta p, then the reflection coefficient is 0. If an unpolarized beam is incident at an angle theta is equal to theta p, the reflected beam will be linearly polarized with its electric vector perpendicular to the plane of incidence at the interface of two different mediums with refractive indices n1 and n2. Polarization by double diffraction. When an unpolarized light beam is incident on a calcite crystal, it usually splits up into two linearly polarized beams. The beam which travels undeviated is known as the ordinary ray or O ray and obeys Snell's law of refraction. On the other hand, the second one, which is generally doesn't obey Snell's law, is known as the extraordinary ray or E ray. The figure 8 represents the schematic diagram of the polarization of light by double diffraction. The appearance of two beams is due to double refraction, and a crystal-like calcite is referred as a double refracting crystal. The velocity of the O ray is same in all directions. So V0 is equal to C by N0 for the O ray, but the velocity of E ray is different in different directions, and the axis along which the two velocities are equal is known as the optic axis of the crystal, and the velocity of E ray is written as VRE is equal to sin square theta divided by C by N E square plus cos square theta divided by C by N0 square for E ray, where NE and N0 are constants of the crystal, and theta is the angle with the optic axis. C by Ne and C by N0 are the velocities of the E ray when it propagates parallel and perpendicular to the optic axis respectively. Polarization by scattering. Polarization also occurs when light is scattered while traveling through a medium. When light strikes the atoms of a material, it will often set the electrons of those atoms into vibration. The vibrating electrons then produce their own electromagnetic wave that is radiated outward in all directions. This newly generated wave strikes the neighboring atoms, forcing their electrons into vibrations at the same original frequency. These vibrating electrons produce another electromagnetic wave that is once more radiated outward in all directions. This absorption and re-emission of light waves causes the light to be scattered about the medium. This scattered light is partially polarized. Example is polarization by scattering is observed as light passes through our atmosphere. The scattered light often produces a glare in the skies as shown in the figure below. Moore's law states that when a perfect polarizer is placed in a polarized beam of light, the intensity I of the light that passes through is given by I is equal to I0 cos square theta I, where I0 is the initial intensity and theta I is the angle between the light's initial polarization direction and the axis of the polarizer. A beam of unpolarized light can be thought of as containing a uniform mixture of linear polarizations at all possible angles. Since the average values of cos square theta is half, the transmission coefficient becomes I divided by I0 is equal to half. In practice, some light is lost in the polarizer and the actual transmission of unpolarized light will be somewhat lower than this, around 38% for Polaroid type polarizers, but considerably high is about 49.9% for some birefringent prism types. If two polarizers are placed one after another, the mutual angle between their polarizing axes gives the value of theta in Moore's law. In X-ray, the Moore's law is defined as I is equal to I0 f by f0 bracketed 1 plus lambda f0 minus f divided by 2c cos square theta I, where f0 is the frequency of the polarized radiation falling on the polarizer, f is the frequency of the radiation passes through polarizer, lambda is the Compton wavelength of electron, and c is the speed of light in vacuum. Applications of polarized light. Polaroids are used in sunglasses. They reduce the intensity and decrease the glare by cutting down the horizontally polarized lights. Polarized light is also useful to determine the size and shape of viruses and also used in infrared spectroscopy. The polarization of cosmic microwave background is being used to study the physics of the early universe. All radio transmitting and receiving antennas are polarized, which is used in radars. AM and FM radios uses vertical polarization while television uses horizontal polarization. Polarization of light is used in ophthalmic instruments to eliminate strong reflection from the patient's cornea, cornea by using 90 degree polarizer. So students, let us summarize what we have learned in this module. This lecture summarizes the fundamentals of light propagation, the physics in the linear optics and nonlinear optics have also been discussed. Ordinarily, a ray of light consists of a mixture of waves vibrating in all the directions perpendicular to its line of propagation. By any means, if the vibration remains constant in a particular direction, then the light is said to be polarized. The unpolarized light has components of light in every direction and could be polarized to have components in a specific direction. The sound waves do not exhibit polarization because they are longitudinal waves. In sound waves, the displacement of the medium is in the same of the opposite to the direction of travel of the wave. This can also be said as the displacement of the medium is parallel to the propagation of the wave. The polarization of light is linearly proportional to the applied field in linear optics, and various processes and techniques are developed to observe the polarized lights and have been discussed in this module. And we have studied the linearly, circularly and elliptically polarized lights. Any system by which light is polarized in a particular direction is transparent only to the light polarized in that direction. Thus, when originally unpolarized light passes successively through two polarizers whose direction of propagation are mutually perpendicular, then the light is completely blocked. The light transmitted by the first polarizer is polarized in a specific direction and is stopped by the second polarizer. If the second polarizer is rotated so that the direction of propagations are no longer perpendicular to the amount of light transmitted gradually increases and becoming brightest when the polarizers are exactly aligned. This property is used in various light filter combinations. The polarization by scattering is observed when light passes through our atmosphere. The instrument used to determine in which the direction of this optical rotation occurs is called a polariscope. We have studied the Moore's law that tells that a perfect polarizer is placed in a polarized beam of light, then the intensity of light can be given by I is equal to I0 cos square theta I, where I0 is the initial intensity and theta I is the angle between light initial polarization direction and the axis of the polarizer. Thank you.